Hello and welcome to NGen Math 6 by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 7, Lesson number 9 on variables related by rates. Now throughout this unit that we've been working with ratios and rates, we've always had two quantities, right? There's always been slices of pizza and kids, or cost and number of gallons of gasoline, right? All of that. Today what we want to do is we really want to kind of formalize it and see if we can maybe, represent the relationship that two quantities have that are related by rates, right? And maybe we want to look at that relationship using tables, graphs, equations, right? Different ways to model and illustrate that relationship. Let's get into it right away in the first exercise. Here we go. Variables are often related by unit rates. These relationships can be represented, as I mentioned, by using tables, equations, and graphs. Exercise number 1. A bathtub is being filled with water at a rate of 12 gallons per minute. The two variables in this problem are the time the tub has been filling, T, and the volume, V, that has filled the tub. Letter A asks us to explain why the volume in the tub depends on how much time it's been filling. Well, this is kind of a little foreshadowing of something we're going to talk about later. But you might just say it's obvious why the volume of water that's entered the tub depends on how much time. And you might simply say something like this. You might just say, the longer the tub fills, the more volume of water that has entered it. Right? I mean, obviously if it's filling at 12 gallons per minute, then, after 0 minutes of filling, nothing has gone in. But after 1 minute of filling, well, 24 gallons have gone in. After 2 minutes of filling, 24 gallons have gone in, etc. And in fact, let's take a look at letter B. How many gallons have filled the tub after 5 minutes? Show your work. Well, again, this should be fairly obvious after everything that we've been doing with ratios, rates, and even what we did in the last lesson on unit conversions. Even though this isn't a unit conversion, right? Really, what we've got is a very similar thing. We've got 12 gallons per 1 minute. We're now going to multiply by 5 minutes. Notice how, again, those units just work out so well. And of course, you probably know that 12 times 5 is 60 gallons. So obviously, if we take that rate, 12 gallons per minute, and we multiply by how much time has elapsed in minutes, it would have to be in minutes, it couldn't be in hours or seconds or anything like that, then we'll find out how many gallons have flown into the bathtub. That's the beautiful thing about having this unit rate, right? Gallons per 1 minute. It's a unit rate. Okay. Well, now let's take a look at letter C. Fill in the table below and plot the relationship between the volume of water in the tub and time. All right, this is pretty easy. I mean, obviously, if no water has flown into the tub because 0 minutes have passed, then the volume is 0. We've already done the second one, right? After 5 minutes, we found that 60 gallons of water have flown into the tank. What I'd like you to do, not the tank, the tub, pause the video now and fill in the rest of this table. It should be pretty easy. All right, well, this is just a ratio table again. So we could literally take this initial ratio where we've doubled the 5 and now we could double the 60, or we could just keep taking that 12 gallons per minute, right, and multiplying it by how much time has passed. So after 10 minutes, 120 gallons have gone in there. And then if I did my 12 and I multiplied it by 15, this one would take us a little bit more time, but we would find 180 gallons have flown in there, right? Now, we'd also like to plot this relationship, right? Where the x-axis, if you will, is the amount of time in minutes, and the y-axis is the volume that has gone into the bathtub in terms of gallons. Actually, I don't know if it was bathtub or a pool. What do we have? Bathtub. Okay, bathtub. I'm going to say that'd be a very small pool. All right, so, after 0 minutes, we have 0 gallons. After 5 minutes, we have 60 gallons. After 10 minutes, we have 120 gallons. And after 15 minutes, we have 180 gallons. And as usual, if we draw a nice straight line, it will pass through all those points. In Math 7, we'll look at this a lot more. We'll talk about what we call proportional relationships. And those relationships in terms of a graph will always go through the origin, and then they'll always lie along a nice straight line like that. All right, let's take a look at letter D. So just to be very clear though, before we get into it, here we're seeing that relationship between the two variables related by that rate, 12 gallons per minute, in a table form. Here we're seeing it in a nice graphical form. Now let's take a look at the final way we represent with an equation. Letter D. Write an equation that relates the volume in the tub, V, to the time it has been filling, T. Now look, back in letter B, right, when my T was 5 minutes, I figured out how much had gone in by doing 12 times my time to give me 60 gallons. Likewise, when I had 10 minutes, right, when that was the value of T, then I did 12 times 10 to get how much had gone in. At 15 minutes, I did 12 times 15 to figure out the volume that I got in. So it appears that every time the volume that goes in there will be just 12 times the amount of time that it's taken, right? And very, very, very often, when we have two variables related by a rate, and we'll see this again and again in today's lesson, you will see that one of them is just equal to the rate times the other one, right? So the volume was equal to that 12 gallons per minute times the time, the number of minutes that we've been filling up the bathtub. All we're doing is, instead of having 10, 15, and 5 in for T, we're just leaving the variable T there instead. Okay, let's look at another problem where two quantities are related by a rate. Now, one thing that came up in the last problem was this idea that the volume of the water that was in the pool, in the bathtub, depended on how much time the water had been flowing. That gets into this idea that in any situation where we've got two variables, we oftentimes have what's called a dependent variable and an independent variable. So with two variables, there's often a variable of a value that depends on the other variable's value. This is called the dependent variable. The other variable is called the independent variable. So the variable, the one whose value depends on the other one, that's dependent. And then the one that's just like, man, I'm happening no matter what, that's the independent variable. So in exercise 1, which variable was the dependent one, which was the independent one? Well, the volume, as we pointed out, depended on the time. So the volume was the dependent variable. And the time was the independent variable. Very often in situations where one of the variables is time, that is the independent variable, and then the other one is dependent, right? And that's often the case because time is just time, right? I mean, time flows along no matter what. Whether we were putting water in that bathtub or not, time just keeps marching along, right? The volume, though, of how much water went into that bathtub depended on the amount of time that we were filling it, right? So time was the independent variable, and the volume depended on how long we were filling it up. All right, let's keep going. Exercise number 3. Dave is taking children to the movies. He plans on buying bags of popcorn that cost $3.75 per bag. Let's pause right now, right? Look at that unit rate, right? And in fact, it's a type of unit rate we've talked about before. That is a unit price or a unit cost. Anyway, $3.75 per bag. Let me finish reading the problem. The two variables in this problem are the number of bags Dave buys B, and the total cost of the popcorn, C. All right, great. Let's take a look at letter A. What would be the total cost, C, if Dave bought 3 bags of popcorn? All right, this is pretty easy. Pause the video now and see how much Dave would spend if he bought 3 bags of popcorn. All right, well, since the popcorn costs $3.75 per bag, figuring out how much he spends for 3 bags is as easy as just doing $3.75 times 3. And of course, for that, we'll get 15, 21, 22, carry the 2, 3, 3, 11, 2 decimal places, so 11.25. Right? Simple enough, and it makes sense, right? I mean, if he's spending $3.75 per bag, and he's got 3 bags, then it should be $3.75 times 3 to give $11.25. Now let's take a look at letter B. Write an equation that relates Dave's total cost, C, in terms of the number of bags of popcorn, B, that he buys. So now, forget about him buying three bags, right? Now let's just say he buys B number of bags, right? The question then becomes, right, what equation will relate his cost, C, to the number of bags, B? Well, take a look at this, right, and see if you can figure out how to extend this with C and B. Pause the video now. Well, right, in this case, B was equal to 3 and C was equal to 11.25. And how did we figure out the value of C? We took B, the number of bags, and we multiplied by $3.75 to get C. And that's the equation, right? The cost will simply be $3.75 times the number of bags of popcorn that Dave buys. There it is. So now if I gave you, 15 bags of popcorn, you could put 15 in for B and then use this formula to calculate C. Or if I gave you, 7 bags of popcorn or 22 bags of popcorn, you could now use this formula to relate the cost to the number of bags. All right, now let's take a look at that whole dependent-independent issue. Just move this out of the way. Letter C. List which is the dependent and which is the independent variable here. All right, so think about this. There are 2 variables. One is the number of bags of popcorn that Dave buys, and the second one is the total cost of the popcorn. Which one was independent and which one was dependent? Pause the video now and think about this a bit. All right, well, the dependent is going to be the total cost, right? So that is going to then depend on the number of bags that Dave buys. You can almost always see the dependent versus the independent by looking at the equation itself. Literally, we are saying to you that this depends, right, on this. So whichever the formula is sort of solved for, you can think of that as being the dependent variable. And the one that's sort of involved in the formula, that is the independent variable. Now, finally, letter D. Dave spent a total of $26.25 on popcorn. Ouch, that's a lot of popcorn. Set up and solve an equation that finds out how many bags B of popcorn he bought. So one of the things about this formula is, you give me the number of bags of popcorn, it's easy to figure out the total cost. But in this case, we've kind of messed with it a little bit, and we've given you the total cost, and we want the number of bags. Let's set up the equation together, right? And then we'll use a little bit of algebra to solve it. Again, we know the value of C. We don't know the value of B. So our equation would look something like this. 26.25, that's our cost, equals 3.75 times B. Now, we've solved equations in this course, right? And we've solved just what are called one-step equations. I need now to solve this for b. I'm currently multiplying b by 375. I want to get rid of that. So what I'll now do is I'll now divide both sides by 375. And now we've got a little bit of decimal division that we have to do. Maybe extend my page a little bit. Easy enough, well, easy enough, right? We need to do this division. Just as a reminder, if I'm doing 2625 and I'm dividing it by 375, the way that I do my decimal division typically is I move the decimal place, right? I move the decimal place until the 3.75 is a whole number. So this is going to be the same as 375 divided into 2625. All right, that's a little bit annoying. One thing, though, that I probably know for certain is that Dave didn't buy a decimal number of bags of popcorn. It's not like he can go up to the counter and say, hey, I need 5.5 bags of popcorn, or I need, 8.3 bags of popcorn. That's not going to happen. So likely, the result of this calculation is going to be a whole number. And we could play around and guess and check on all of that, but I'll tell you right now, it's going to be 7. And let's just verify that really quick by doing 7 times 375. 7 times 5 is 35, carry the 3. 7 times 7 is 49, plus 3 is 52, carry the 5. 7 times 3 is 21, plus 5 is 26. And there it is. So B is equal to 7. Dave bought 7 bags of popcorn. Dave's a good person. Takes the kids to the movies, right? And there's a lot of kids he took. 7 kids, or maybe 6 kids, and then he bought a bag of popcorn for himself. All right, let's take a look at one last problem. Here we go. We got to have a graph, right? You got to have a graph. So exercise number 4. Angelia is taking a walk. The graph shown below shows the distance she has walked in feet compared with the amount of time she has been walking in seconds. How far has Angelina walked in 10 seconds? That's not so hard. Why don't you pause the video now, just read from the graph how far Angelina has walked in 10 seconds, and don't forget to include units, okay? All right, well, simple enough to read this off from the graph. We go down to the time down here, 10 seconds. We come up to the graph, we go across, and Angelia has walked 65 feet in those 10 seconds. All right, let's take a look at letter B. Using A, at what unit rate, it should say, what is the unit rate that Angelia is walking at? Use proper units. All right, actually, no, that's correct. At what unit rate is Angelina walking at? Anyway, whatever. Let's figure out the unit rate that Angelia is walking at. Now, in order to do that, right, as always, what we're going to do is we're going to take our 65 feet and we're going to divide it by 10 seconds, right? Keep in mind that what we're looking for here is the speed, all right? So what is 65 feet divided by 10 seconds? Pause the video now and remember, multiplication and division by 10 or powers of 10 should be pretty easy. Take a moment to figure out what this is equal to. All right, well, when you divide by 10, you can simply move the decimal point 1 unit to the left, and we'll get 6.5 feet per second. 6.5 feet per second. That's your speed. That's a brisk walk, 6.5 feet per second. It's a few more than 2 yards per second. Anyway, our final question, which of the two variables, d, the distance, or t, the time, is the dependent variable? All right, well, what do you think? Pause the video now and write down which one you believe is the dependent variable. All right, well, as usual, when we have two variables and one of them is time, time is almost always the independent variable. Again, I don't want to say that it's always the independent variable. there could be a situation where time is dependent. But in this situation, right, then the dependent variable is the distance. I'm going to write that out, distance d. And it's not because it begins with the letter D. It's because literally how far she's walked depends on how long she's been walking, right? How far she's walked depends on the amount of time she's been walking. So time is independent. It just kind of goes on, but the distance, the other variable, is the dependent one. All right, let's wrap this up. Very, very often, when we have something occurring at a constant rate, and that could be a constant speed, it could be a constant price per something, right? When we have this, we can then relate the two variables involved. Like in the first exercise, it was the volume of water that had entered into a bathtub and the amount of time that the faucet had been on, right? And we can relate those two through the use of tables, graphs, and equations, all right? And all of them should kind of make sense from the perspective of what we've been working on with rates and ratios, all right? We'll see a lot more with independent and dependent variables as we move forward in mathematics. For now, I just want to thank you for joining me for another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.